This is an instructional video for high-pressure die casting process simulating with sleeve. First, execute any pre to set the simulation condition. There are two ways to import STL files. Let's start with the first way. Click File and click Import to import the STL file. Import is a function that loads the saved modeling in STL format into any pre. Another way to import STL files is very simple. Simply just drag the STL file to any pre. Deactivate the mold entity to make sure that the imported STL file is loaded correctly. For high-pressure die casting analysis including sleeve, each STL file of sleeve gate, sleeve, piston, sleeve mold, and cavity mold are additionally required in addition to runner, overflow, and cavity. Set plunger tip, also known as piston, as attached. When you simulate a real model of in-gate or runner, you can integrate it into runner. Now sap mold with sap mold. Casting only function is only used for flow analysis without mold, and is not used for general casting. Casting plus mold is used when simulating cavity and mold. When you click the Casting plus mold button, you will see three different options. First of all, box is to create a virtual space. Please input the thickness of each direction. Second of all, shell thickness option will be enabled when you input shell thickness for investment casting. Lastly, mold entity is used when there is mold STL. Make cast from the cavity of mold is a function that recognizes the rest of the mold as cast when there is no cavity but mold data. In other words, if there is cast entity, even when you check this function, simulation will not be proceeded. In this case, since there is mold STL, please select mold entity. There are three ways to generate mesh, which are build uniform mesh, build variable mesh, and auto mesh. First is build variable mesh. Press the spacebar to switch the mode to selection mode. Then select Start and End. After entering dividing number, set the remaining part as auto block. Mesh will be generated in the orthogonal direction of the selected axis. Set the rest of the Y and Z axis. Mesh generation cannot be executed on the forwarded axis displayed on the screen when generating mesh. After setting X, Y, and Z axis, click OK button to generate mesh. When analyzing sleeve, it is suggested that you generate mesh based on runner and generate one mesh per 2 to 3 millimeters. Secondly, we'll look into uniform mesh. In the uniform mesh, there are a total number of cells dividing the simulation area into a fixed size mesh when the number of all cells is input. Also, there is number of cells along axis, which specifies the number of mesh in each axis direction, and size of unicell that specifies one cell size. Size of cell is a function that decides the mesh size of X, Y, and Z directions. The total number of mesh will be generated automatically by the program based on the values entered by the user. The last one is auto mesh. Click auto meshing. For X, Y, and Z, after setting the minimum and the maximum size of auto mesh. minimum and maximum size as the reference value of the generated mesh size. Let's start with task design. After selecting the process, please select the range of simulation. In the material setting, double-click the entity to select the material. Multiple selections can also be made by pressing the Ctrl or Shift key. In initial condition, enter the initial temperature of each entity. The initial temperature here states the temperature before the simulation starts. Heat transfer coefficient value is input automatically, but please make sure if the value is right or not. The heat transfer coefficient unit of this video is calorie. Set pouring temperature in gate condition. Input pouring temperature and pouring speed only, since leaf gate is included in entity. Pouring speed here is not the filling speed into the cavity, but the melt pouring speed of the sleeve based on sleeve gate. To set gravity force, please click Enable and set the gravity direction. The gravity direction is based on the axis displayed on the screen. Activate turbulence model to calculate turbulence field. We suggest that you use turbulence model for high-pressure die casting. Gas and melt surface is a function that predicts the amount and the position of the generated gas when melt is poured into the cavity. Oxide slide inclusion model is a function to set oxide occur conditions and to predict oxide dispersion in cavity. After activating it, click the icon next to variable temperature to see the value of the automatic input. Particle tracing is a function to track the movement path by expressing the melt as particles coming through gate. Click to enable Start/End control. For particle source value, 10 is recommended. In the case of high-pressure die casting, it is common to set it to bi-filling rate because the pouring time is short. Shrinkage model is a model for predicting solidification shrinkage. For high-pressure die casting process, gravity shrinkage is not considered. Sleeve model sets the high/low speed length of sleeve, as well as speed and time of the sleeve by entering the conditions of die casting equipment. In the sleeve tab, set the sleeve length, diameter, and biscuit thickness. Sleeve length value should include the thickness of biscuit. Melt charging is a setting of the melt in the sleeve, which is automatic setting and will be passed after confirmation. In Shot tab, set the speed and length at low/high speed. When analyzing high-pressure die casting, including sleeve, set the plunger movement in Plunger tab. Activate Enable Plunger Moving and select Attach a Piston Entity in Plunger. Set the direction that plunger should move. Please select the direction based on the axis displayed on the screen. Select the following two options. First, Assume that the melt is filled in the sleeve. Second, this is an analysis that begins with filling into sleeve from the actual ladle. To use this option, you must input the pouring speed and gate condition. Lastly, set the time that piston moves after filling into sleeve. Activate both mold erosion, that predicts mold erosion area, and gate flow tracking, which shows the flow of melt from in-gate and gate. After setting in/out condition, click Save, then presetting process will all be done. In general for end condition, please select 100% solidification. However, this can vary depending on the test design setting. The information shows in progress result are temperature, oxide, velocity, flow tracking, and these can be checked only according to the output interval set in output condition. When setting is done on any pre, and the file is saved, 8 files will be created in the folder. When setting is done on any pre, and the file is saved, 8 files will be created in the folder. If the extension is GSCX, it is the file that contains some contents from AnyPre. MIF6X is virtual mesh information on real flow. Therefore, if you delete it, real flow will not be applied. MSHX includes physical mesh information. PRPX is a solver execution file. PXM, XML, TXT, and VPX are the files that store information about simulation settings. X after the file name means 64-bit. Save it via AnyPre to proceed to simulation, or you can also execute AnySolver for simulation. After executing AnySolver, click Open Project to open the file. Then, the information window will appear about the space available on disk, space required on disk, and number of result files. Please click Start after confirming the information and proceed the simulation. Can be observed via AnyPost when the simulation is done via AnySolver. There are 2 ways to run the simulation file. First, execute AnyPost and then click File Open Project to load RLTX file. Second, drag the RLTX file to AnyPost to load the file. Create real shape to map the cap model to the mesh-like result and see it in real shape. However, the real shape only applies to cast entity. In order to observe entity other than the cast entity, you need to deactivate the real shape. The results that can be checked in AnyPost are final result and progress result. In final result, you can observe the changes during the entire simulation process. In progress result, you can observe the temperature, pressure, and speed values set by the user. Final result consists of history data to observe the flow and solidification pattern result. Simple shrinkage analysis to observe temperature gradient and cooling rate. Advanced casting analysis to observe pressure distribution. Microstructure prediction and mechanical properties. Click Filling Sequence in History Data tab to check the filling pattern. You can check the overall filling pattern and the final filling area. You can continuously observe the final solidification time with solidification time. And solidification sequence shows all the solidification process by time, and especially the area where remelting occurs. When observing the solidification pattern, it is recommended to observe an inverse contour. Predict the area where shrinkage defects could occur by focusing on observing the final solidification area in the product. To observe macro shrinkage, please select Probabilistic Defect Parameter in Advanced Casting Analysis tab. Please select Retain Melt Surface Area in Defect Parameter and use the cross-section view function to observe macro shrinkage inside the product. At this time, the shown shrinkage is a probability distribution, not a size. For micro shrinkage, please select Combined Defect Parameter in Advanced Casting Analysis tab. After selecting Niyama, please select Defect Parameter as Combined Defect Parameter and Probabilistic Defect Parameter and observe micro shrinkage inside the product with cross-section view. In the case of micro shrinkage, user can observe any results by using 3 parameters. Air pressure is a model that predicts the pressure distribution of the entrapped air in the product after filling is completed. It can observe entrapped air defect area by considering the division of bond and mold. Mold erosion predicts the erosion area of the mold by analyzing the velocity and incidence angle of melt. Progress result shows the result depending on output condition step that user set in any pre. User can select and observe specific result out of temperature, pressure, velocity, gauge flow tracking, viscosity, and gas entrapment. Temperature is melt temperature during filling and solidification. Gauge flow tracking is the amount of melt coming from each ingate, which is color-coded. Gas entrapment is gas volume and distribution in melt during filling. Please refer to user manual for fine adjustment or data export when observing other results.